Hi, welcome back. This is Professor Merrill Lichty. In this video, I'm going to cover confidence intervals for the mean. This is actually the first part of a two-part video series. And the problem that we are faced with is estimating the unknown population mean mu. And all we have to do that with is sample data. And the sample mean x bar is kind of the logical point estimator for mu. And you'd say, what's a point estimator? Well, it's a single point. If someone were to say, given the data that you have, what's your best guess? You would just say x bar. But that does not take into account how accurate the estimator is. And so instead of giving just a single point estimator, we're going to use what's called a confidence interval or an interval estimator. And this allows us to make statements about how accurate the estimate is. The logic of confidence intervals comes from the fact that, first of all, x bar is going to be at least approximately normally distributed. So in other words, the population is normal or the sample size is bigger than 30. And the empirical rule tells us that about 95% of the time, the x bar is going to be within about 2 standard deviations of mu. So we would say a 2 standard deviation interval around x bar will contain mu about 95% of the time. And so we can write down the 95% confidence interval as x bar plus or minus 2 times sigma over the square root of n. What this means is x bar is our point estimate or point estimator for mu, and sigma over the square root of n, you'll remember, is the standard deviation of the point estimator, or the standard error of x bar. So the way to interpret the 95% confidence is to say, like a lot of the other things we do in statistics where we're going to do things over and over and over again in the long run, we would say 95% of the intervals that are computed will actually contain the target parameter, which means 5% of the time when we make these intervals, we're not going to have the true value of the parameter inside the interval. And you might say, well, what if 5% is not an acceptable failure rate? Then you can change the level of confidence to 99% or to some other value that you are comfortable with. So let's look at an example problem. Suppose we'd like to estimate the mean diameter of piston rings that are processed in some factory somewhere. And we've done this for a long time, and so the experience that we have allows us to know that the standard deviation sigma is 0.0025 millimeters. We're going to take a sample of size 50, and from that sample we get x bar, which is equal to 10.0831 millimeters, and we want to find a 95% confidence interval for mu. So reviewing this, let's pull out the numbers. We have n is 50, sigma is 0.0025 millimeters, x bar is 10.0831 millimeters, and we want a 95% confidence interval for the mean mu. So we can just plug these numbers into our formula, just plug and chug, and we get 10.0831 plus or minus 0.000701 for an interval of 10.082393 on the low end, and on the high end 10.083807. And we would state that we're 95% confident that the population mean mu is somewhere between 10.024 and 10.0838. Sorry, that's 10.0824 and 10.0838 with some rounding done. And this 0.007071 is sometimes called a margin of error or an upper bound for the estimator. In other words, at the 95% level, confidence level, we would say that the most the error is we should expect to see is 0.007071. Now we took this value of 2 from the empirical rule that says there's a 95% confidence or coverage level, and that is approximate. So let's do this a little bit more precisely. So we want to use a z-value to find the exact number of standard deviations to give us 95% confidence. In other words, if we drew the normal distribution, we said 0's in the middle, what value of z has 95% of the area in the middle? In other words, we want 2.5% in each of the tails. And we can look these numbers up and find that we have negative 1.96 and 1.96. And I'll refer you back to last week's material where we looked at the normal table, or we used Excel or Minitab to find that value of 1.96. So that means a more accurate confidence interval would be x bar plus or minus 1.96 times sigma over the squared of n. And so we get 10.082407 and 10.083793, which are not that different from the rounded values that we found by using the empirical rule. And here those values are to more than 3 or 4 decimal places. So you can see how close this is. Okay, what if 95% is not good enough? We can use a 99% interval. This interval will be wider. That may seem a little counterintuitive, but in fact it's true. And it's wider because the z-value that we use corresponds to having 99% of the data in the middle, so 0.5% in each of the tails, and that happens at plus or minus 2.576. If you're going to use software, that's the number you should come up with. If you're going to use the table in the book, you would be somewhere between 2.57, 2.58. So you take the middle of those if you like, or any of those numbers should work. And you can see that the interval is bigger, 10.0822 on the low end and 10.084 on the high end. And that's what we have for this video.